Hello everybody, welcome to another natural resources lecture. Today we are discussing energy flow and chemical cycling. So let's start off with where everything starts off in terms of our energy flow. Everything comes from the sun. It is the source of virtually all the energy in the biosphere. The sun with its radiant energy heats the earth, causes our winds, evaporates water, and basically makes everything on this planet function. It is the beginning. It is the source of energy that allows the earth to move and do what it needs to do in order to provide life for us. And down here in the bottom right, I have a link to some NASA information to give you a little bit more information about the sun. So you can go ahead and pause the video and bring up the lecture slides and click on that and look at that information. So almost all of Earth's energy output comes from the sun. The basics of this process. The radiant energy from the sun is released. So it takes, if we're talking about to try and put into perspective how big the sun is and how complicated this energy process is, it takes about 150,000 years for energy that starts in the sun's core to make its way to the solar surface of the sun. So it starts in the core. It takes about 150,000 years for that energy to work its way out, and then that energy is so powerful that it travels 93 million miles to Earth, and it does that at the speed of light, which is just over 8 minutes for it to travel 93 million miles. And so that radiant energy, that speed is 186,000 miles per second. And that's what's known as the speed of light, is 186,000 miles per second, because it takes 8 minutes for 93 million miles to be traveled by the sun's energy. And so the sun's energy, the sun's radiant energy, that's what we know of as the electromagnetic spectrum, and that goes all the way from low energy radio waves to high energy gamma rays. And the part that we're usually most concerned with is the idea of the visible light spectrum part of the electromagnetic spectrum, which is this part right here on this infographic. That's where we get the colors, different colors that we see. And then I've included a little YouTube video link right here for those of you who have ever asked the question, why is the sky blue? The answer is Rayleigh scattering, and it'll go into what that is. So why start with the sun, and why is that radiant energy important to us? Well, it's not only is the light that we get and the energy that we get important to us, but also the energy that that we don't get is just as important. So the incoming solar energy, we get about 2/3 of it. The other third is going to be reflected off of different things like clouds, dust, the surface hitting things and then bouncing back, and that part that gets reflected, that's called albedo. So albedo is the average reflection of an object. The Earth's albedo is the reflection of light into space from the Earth, and so about 2/3 of our light gets absorbed, and about 1/3 of it gets reflected. So the Earth's albedo is around 1/3 or 33%, give or take. Now, in this infographic here showing Greenland, it shows some of the different albedo effects. So with the snow, you get about 90% reflected, and only 10% is taken in, and the same thing with the opposites happens actually in the ocean. 90% is absorbed and 10% is reflected. On the ground, you get about 60% absorbed and 40% reflected. And so it's just it's interesting because you think of the idea of the sun's energy coming and you think, okay, well, we get all of that. Well, we don't actually get all that. There's a lot of it that's reflected. And so here's a video that goes into albedo a little bit more. And so just kind of another picture trying to paint this idea of albedo. So if you have forest covers, you get about 80% absorbed, 80-90% absorbed, 10% reflected. Crops and grasslands, 75 to 90% absorbed. Grasses, 70 to 75%. And then you look at some things like asphalt, blacktop. You're getting a lot of absorption. So if you've ever sat there and you go, wow, you know, the blacktop's really hot today, or the road just seems really hot, or you see like heat coming off of the road. It's because it absorbs the sun's radiant energy really, really well. Water, it can be completely different, and it varies with the sun's altitude. You can get a lot of different amounts of albedo in terms of water. But overall, our average is around 30%. Oops, one too far. There we go. So why is the albedo important? It's because of the greenhouse effect. And so with the greenhouse effect, that is how this plant stays warm. That is how this planet is warm enough for us to live on it. So what happens is the solar energy from the sun gets absorbed. What energy isn't absorbed is reflected back into space. But we have our atmosphere, the ozone layer, and greenhouse molecules surrounding our planet. So what happens is, as that albedo, as all that light gets reflected back into space, it hits the atmosphere and it starts to bounce back and forth, or kind of ping pong back and forth off the atmosphere. And this constant back and forth is what actually heats up the planet. So not only is it what's absorbed just from the sun, but then also this extra added in greenhouse effect, where we get that extra bump of energy being absorbed. That's actually what really heats up the earth. So without the greenhouse effect to trap that extra radiant heat, the average temperature on the Earth's surface would be about 0 degrees. But with the greenhouse effect, Earth's average temperature is about 57 degrees. So it really is, it's important. Not only is the energy that we get directly from the sun important, but this energy that's reflected off is also just as important because of the greenhouse effect. And it's called the greenhouse effect because if you are familiar with a greenhouse, the way that it works is a greenhouse is mostly windows so that light can come in, but then also once the light is in, the light is then trapped in there and keeps everything warm. So when you have a greenhouse for plants, it's an area that's going to provide some humidity, provide some warmth, so that the plants aren't subject to the cold weather outside of the greenhouse because of the way that it's designed. So our atmosphere gives us that greenhouse effect by allowing the energy to come in, but then also keeping it trapped in there and not allowing it to escape out easily. Now, another thing to really think about with the greenhouse effect is the idea of the problems that we're having in terms of climate change, and people talking about holes in the ozone layer and emissions and all these other things. So why are those a big deal? Well, the idea is the more emissions that we put out there, the more for lack of a better term, junk, or just molecules and particulates and particles that are up in the atmosphere. And what that's going to do is that's going to create more, in some cases, more reflection in some areas, less absorption, and more albedo in some areas. In some places, it's where it's maybe put a hole in the ozone layer. Now we might be getting more absorption, but then we're also getting more albedo as well. And so when you look at climate change, people think of climate change and they think, oh, well, the Earth's getting hotter, because they just think of the idea of global warming. But the idea of climate change is that now we're getting all these wild swings, and sometimes it's hotter in a place than it used to be way earlier or way later, and sometimes it's colder than it's supposed to be, and we're getting all these weird swings, and it's partially due to this idea of these problems that we have with the emissions that we're putting out, and with just this basic idea of the sun's radiant energy and how it affects the Earth's surface. So more air particles, more reflectivity, you get more solar energy reflected away, and you could end up with colder temperatures. When you have big, huge events like volcano explosions and things like that, it changes the weather for quite a bit. Could even change the climate if it's a big enough event. People talk about that with some events in history, like the explosion of Krakatoa, where a volcano explosion basically sank a whole island, and was a big enough explosion that it changed the weather for like months or even years. And it's really interesting the way that just this simple balance of air particles could really change things. And on a simpler note, just think about the idea of how different you feel on a completely sunny day with nothing up above you versus a cloudy day, and that feeling that you get that when you have a cloud above, how it feels in terms of, oh, it's a little bit cooler or colder or better, and then all of a sudden that cloud passes and you get hit by the sun and you're like, oh man, it's so hot. Like that difference it makes, that's really, that is what's happening at all times. But we got a lot of little tiny particles happening, and if we have more tiny particles, that can be problematic. If we keep punching holes in the ozone layer, that can be problematic. So it's really the idea of trying to limit our pollution, limit these emissions, to really make sure that we keep this nice balance that we have with our greenhouse effect, in order to make sure that this planet is healthy and gets the energy that it needs in order to function correctly. Oops. All right. Let's talk about photosynthesis then. So, why is it important to have the sun providing us so much radiant energy? It's because it's one of the three things needed for the photosynthetic process. So photosynthesis is the process in which plants capture light and convert the sun's solar energy into sugars and release oxygen into the atmosphere. And this process is what sustains and supports life on Earth. So the idea simply is just sunlight, carbon dioxide, water, and your output is glucose or sugar or energy and oxygen. So just the basics. We're taking the sun's radiant energy, and now we are putting it into and converting it into energy through the process of photosynthesis. Yes, there's formulas that you can memorize. That's great for the other classes. You don't need to know it here. But what do need to understand about photosynthesis is just the basics of it. It's a combination of sunlight, carbon dioxide, which is in our atmosphere, and then water. And that combination of things allows us to get oxygen on the oxygen as an output, and that's comes with the simple understanding of if we have carbon dioxide or CO2 going in and we've got O2 coming out, that means that the carbon is staying with the plant. And so the carbon is getting stored by the plant. We get oxygen, which we need to breathe, so that works out great for us. So having plants and trees and grass and all these things that do photosynthesis are really helpful for us because they provide us oxygen. And then there's glucose or sugar that comes out, which also is good because we eat plants. And then there's also other animals that eat plants that we also like to eat. So there's this continued transfer of energy all the way from the sun to these plants and then to what's eating those plants. So then we also have cellular respiration. Cellular respiration is the breakdown of organic molecules into energy needed to meet the cellular needs of plants and animal cells. ATP is molecular energy storage. Or, let's kind of simplify that. It's the process through which cells convert the sugar to energy. So now that the plant is doing photosynthesis and taking in this energy, it needs to have its cells convert that sugar, that glucose that's created, into energy. And so that's cellular respiration is that process. So we look at our little diagram here, and we got our carbon dioxide and water. We add that with sunlight. We get photosynthesis. Photosynthesis gives us glucose and oxygen that allows animals, one of which we are, to breathe and to have energy. So we take that in, we give off heat, we do cellular respiration, and then we give it back. Seems simple enough. So the balance between photosynthesis and cellular respiration, where we're converting that sugar and using that sugar and giving it off, that balance is essential for life on Earth. It's just this balance between the energy that we're taking in and creating and then the energy that we're giving off in return. And that takes us to the idea of gross primary production. Now, gross primary production is just simply the total amount of organic matter produced by the photosynthetic process. So the sun gives plants energy, the plants grow and produce, and all that is produced by that photosynthetic process, that's what is called gross primary production. So then what we have is net primary production as well. And net primary production is the chemical energy still available in plants after cellular respiration, because the plants have to use some energy to be able to grow. And so whatever is left over, that is net primary production, and that, or what you can kind of just term at and look at as food. And there's just a simple math equation of net primary production equals gross primary production, the total amount of energy produced through photosynthesis, minus the cellular respiration, the using of that energy to grow, gives us net primary productivity. And that net primary productivity, if you want a little bit more, we've got some NASA information that you can read up on that link. So then you'll hear things like save the rainforest and that estuaries and these other places that you might not know really what they are, but you know that they are, people say that they're important. Well, why are these places important? And it's because of the amount of net primary productivity available in these places. So when we look at estuaries and swamps and marshes and tropical rainforests and temperate forests, or what most people just think of as forest, that is where we get our highest amounts of net primary productivity, or where our highest amounts of plants and food and things created through photosynthesis are then available to all the plants and animals. So these areas are teeming with biodiversity, with lots of different species, because there's lots of different food sources available in these areas. This is usually influenced by rainfall and temperature, and that becomes important when we're looking to classify areas, which we'll discuss in a future lecture. High productivity occurs when there's a year-round growing season, such as a warm and humid forest. So the closer these places are to where it can be warm and wet all the time, the more productive they're going to be. Low productivity occurs when there's slower growth, such as in cold, dry tundra areas. So where do we see low growth, low productivity? We see it in the tundra, we see it in the deserts, see it in the open ocean, or places where you don't get a lot of, you either don't have a lot of precipitation or it's very cold. So temperature and rainfall or precipitation are going to become very important ideas when we're thinking about ecosystems and how they function and how they produce. So the big thing to really understand with these areas and their high net primary productivity is that if you have areas where you've got a lot available in terms of food and plants and trees and all of that in an ecosystem, then that is going to basically open up a lot of habitat, a lot of food source options, a lot of chances for animals to survive. And that's really what a lot of species are looking for, just a chance to survive. And so where do we see a lot of our primary productivity? Well, as we get closer to the equator, you see a lot more primary productivity, just because you get that idea of that warm and humid or high levels of precipitation plus high temperatures. Now, if you look here, you say, well, that's decently close to the equator and there's not much happening there. Well, that's because that's the Sahara Desert. So yes, you do get, if you get areas that don't get that rainfall, then yes, you're not going to get high primary productivity happening in those areas. So now we've got an idea of how we get food and how food is created in the ecosystem. So what happens next? So simplistically, how does energy flow through an ecosystem? We've mentioned this term before, but let's talk about it again. The basic pattern of energy flow among organisms through an ecosystem is called the trophic structure. So our trophic structure is how energy will flow through the ecosystem. So simplistically, we start off in this diagram with the sun. The sun provides us radiant energy traveling at the speed of light, hits the surface. Plants, forests absorb that energy, and the energy that gets reflected off then starts ping-ponging back and forth and heating up the earth. So we use that energy, plus the producers are using the energy that was absorbed and combining it with carbon dioxide and water to produce photosynthesis and give off glucose or energy, and then also giving us oxygen to breathe. So those plants, organisms that can do photosynthesis, those are called producers. So grass, shrubs, trees, algae, any of these things that can do photosynthesis, take radiant energy from the sun, combine it with carbon dioxide and water, those are producers. The producers are then ate by consumers. The producers, the parts that don't get used or get shriveled up and become old, then becomes decomposed, falls to the ground, and that'll be used up by decomposers. The consumers also will then have waste products, feces and whatnot, and also some will die and some will get eaten by other consumers, and those then will also contribute to things that get ate by decomposers. And all three of these things are giving off heat energy, and in that transfer of energy among this ecosystem chain. So that is our basic trophic structure, but let's try to apply it a little bit more. So we have our energy source, we have our producers. Another way to say producers are autotrophs, and they're producing our net primary productivity, and we might get some organic matter from the soil added in there. We also will get some organic matter leaving, and then all of that gets ate by our heterotrophs, or our consumers, and through our cellular respiration we're giving off heat the whole time, and then we will contribute back to the producers through nutrient cycling, so through what's going on in the ground. That's going to be the second part of what we talk about in the lecture today, is this idea of chemical cycling and nutrient cycling. So our types of consumers. So we have 4 types of consumers. We have herbivores, they eat plants; carnivores, they eat meat; omnivores, they eat plants and meat; and then detritivores that get their energy from dead matter or organic waste. And among our detritivores, we actually have 2 categories. We have decomposers and we have scavengers. So with our herbivores, easy examples: horses, rabbits, cows. Our carnivores, lions, snakes. Our omnivores, humans and bears. Our detritivores, we've got decomposers, so bacteria and fungi are ones that that cause decay to happen. And then we also have scavengers like vultures and ants that feed off dead or decaying matter. Just think about the idea, if you ever dropped any food outside and then all of a sudden you leave it and then you come back a couple days later and then all of a sudden there's ants, hundreds and thousands of ants all over it. That's because they're scavengers and they're detritivores. That's how they get their energy, is off of dead matter. So looking at our trophic structure again, or our food chain, we get the sun providing energy to our our producers. Our producer is then ate by this grasshopper, who's our primary consumer. The grasshopper is then ate by this secondary consumer, the frog. The frog is then ate by the snake. The snake's then ate by the hawk. The hawk then either poops out what it doesn't use, or the hawk eventually dies, and then that will get decomposed by the fungi and bacteria. Too far. There we go. So, food chain or trophic structure, either term is fine. They're both they both mean the same thing. It's the progression of organisms through which energy and nutrients flow. That's going to be our definition of food chain or trophic structure. The progression of organisms through which energy and nutrients flow. Each level is known as a trophic level. Trophic level within our trophic structure. Primary producers are the first trophic level, and then it goes up from there. And so on the left here, we have a plant as our primary producer. That plant is ate by an herbivore, which is this grasshopper. That grasshopper is then ate by a carnivore, which is this mouse of some kind. This mouse is then ate by a secondary consumer carnivore, which is this snake. This would be your primary consumer, secondary consumer, tertiary consumer, and then your quaternary consumer is this probably a hawk, I would say, that then takes out this snake. We can see this also happening in the ocean. Our phytoplankton produces photosynthesis. That's ate by our zooplankton. The zooplankton is then ate by the, let's just call it small fish, by the bigger fish, by the really big fish. or the orca, depending on how you want to call it. Food chains are the easier way to think about it, but really it's more like a food web, because it's really more of a complex process. It's not as clean sometimes as it seems, but it is it's a little bit complex, the way that some of these things are ate by some of these other things, and then they all are pooping and contributing back into the soil. So it's much more of a food web than it is just the simplistic food chain. It's the interconnected series of food chains, or all these trophic structures added together, that really we see much more of a food web. So the most obvious example for me, or the one that I'm going to try and make to you as the most obvious example of trophic structure and of a trophic cascade, is this this Yellowstone idea, and the taking away of the gray wolf. So the gray wolf is taken out of the trophic structure, taken out of the food chain in the 1920s, and that leads to a trophic cascade, as it says right here. So that trophic cascade means that the problems of having that that keystone species leave the food chain, it created a bunch of ripple effects down the trophic structure. So, whoops, let's go back real quick. So as we look right here, elk populations without their primary predator resulted in severe overgrazing of willow and aspen needed by beavers for food and shelter during dam building. Various scavenger species suffered because there weren't the year-round wolf kills. They weren't able to feed on the leftovers that they have. So without wolves, the coyotes became the apex predator, and then that caused problems with the antelope, red fox, and rodent populations, and birds that prey on small animals. And then our beavers virtually disappeared from their northern range. They had their dams disintegrated, marshy ponds became streams. We lost more willows and aspens, had heavy stream erosion. Many plants and animal species were affected. But then, in bringing back the gray wolf and having the great fires of 1988, which kind of reset a lot of the ecosystem, we were able to see kind of a recovery. So we get beaver colonies increased, elk numbers dropped, coyote numbers dropped by half, antelope, rodent, fox populations increased. And so really this trophic cascade brings to the forefront the idea of keystone species. And so I've got a video right here about beavers and how beavers are a keystone species in a lot of ecosystems, as well as apex predators like the gray wolf. So it's a topic that we'll come back to, but definitely something to really understand when we're talking about trophic structure and food chains and energy flow, is the importance of keystone species within different ecosystems. This energy flow is a pyramid. So we have a lot of producers. If we look at this graphic here, there's a lot of producers. If you really think about blades of grass and how many trees there are on this planet, there is a lot. There's more trees on this planet than there are stars in our galaxy. So there's really more out there than you think. And if you say, well, that's a huge number, it is. Now think if you counted every single individual blade of grass and every single shrub that's out there. So there's this huge amount of producers because the sun provides us radiant energy. We get that, we have photosynthesis happening, and that's how we sustain life on Earth. That's where we get all of our energy from. Then we have a bunch of primary consumers. We have fewer secondary consumers. We have fewer tertiary consumers, and you get this, you get less and less as you get to the top. It's widest at the bottom in terms of this this pyramid idea of the food chain, because there are more producers than there are consumers. And that's a good thing, because if you get more consumers, then you get producers, you will have less output, and that really would cause huge problems. And so that would really start limiting the numbers of species. It really emphasizes how few top-level consumers can be supported by an ecosystem, because if you start to have it to where this out here starts being larger than any of these other parts, the system starts to fall apart because it's going to be out of whack. You need to have enough production happening to match your demand. So then, what problems can we see, or what problems can we have happen besides the idea of a trophic cascade and removing part of the food chain? Another thing that you could have happen that can be problematic is the idea of ecosystem simplification, which occurs when species are eliminated from an ecosystem and generally become more vulnerable to disturbances. So this is what happens, or is something to worry about with the idea of large-scale agriculture. Because what we're doing is we're taking all the biodiversity out of an area and we're simplifying it to one crop or just a couple crops. And so let's take the Irish potato famine as an example. So we've got a potato field, and so we had the Irish potato famine. So you had weather conditions that favored a fungal pathogen called potato blight. The potato blight wipes out the majority of the potato crop. That causes mass starvation and actually forces people to leave Ireland and come and go find somewhere else to live because they cannot grow this crop that they were totally dependent on because they had simplified their ecosystem. They said they loved potatoes. Potatoes were great. They're making potatoes, and then all of a sudden, if potatoes aren't there, what do? How do you function? And so that actually led to more than 1 million Irish starving to death, and then more than 1 million Irish leaving to move to the United States. And so it's really interesting when you think about ecosystem simplification. So that's kind of a big historical idea behind ecosystem simplification, but it happens all the time. It happens a lot too with the idea of an invasive species moving in. So an invasive species comes in and takes over an area where, you know, you might have had trees and shrubs and grass, and now you just have this one species there. Any animals that live there, any people who were dependent on the crops or whatever that were in this area now just say, well, I either have to figure out how to use this species that is now taking over this area, or I've got to get rid of the species, or I've got to go somewhere else. You're very limited on your choices when you have to deal with this idea of ecosystem simplification, when there's a lot of different things to choose from. If the idea that, well, potatoes aren't available, but I've got lettuce and I've got corn and I've got all these other things, no big deal. But if it's all the same and it all disappears, that's where it becomes really problematic. Too far. There we go. So the second part. So we talked about energy flow now, the idea of how we get energy from the sun and it works its way all the way to us and all the other animals on the planet. But how do we then contribute back to it? And that's through what's called nutrient cycling. So we talked about the idea of cellular respiration coming from both our producers and our consumers. So that cellular respiration then goes back and becomes CO2 in the atmosphere. That, along with the emissions from burning wood and fossil fuels, also coming from our detritivores, all of that comes back into the atmosphere or into the soil, and then gets cycled back into the system. So nutrients are not created or destroyed, just like our laws of thermodynamics. Energy is not created or destroyed. It's just changed into different forms. So we have this circular flow of an element from abiotic form or non-living into a biotic form. And then it's released back into the environment and becomes abiotic again. So the majority of our atmosphere on this planet is actually nitrogen. 80% basically. It's probably, I guess technically it's more like 78 or something like that, but we'll say roughly 80% of our atmosphere is actually this abiotic N2 gas form of nitrogen. And so what we have to do is we have to have some sort of process that can then take all this nitrogen that we have in the atmosphere and use it, because we know how to use the carbon dioxide that goes back into the atmosphere, that gets back into the photosynthetic process. But what happens to the nitrogen that is released and then just put into the atmosphere? We need to have some way of fixing it or converting it from this abiotic form or non-living form to a biotic or living or usable form of nitrogen. So we get our N2 then becoming nitrate or NO3. And there's two ways that we fix it or turn it into a usable form. And that's atmospheric fixation and biological fixation. So how do we do those two things? Well, atmospheric fixation happens rather quickly through a process like lightning hitting the ground. That is one way to easily get this nitrogen in this gaseous form in the atmosphere to then be put into the ground, into this usable form that we can then use it as a living form of nitrogen. Another way is through plants and through legumes. So that's our biological fixation. Legumes or Fabaceae or the bean family, the pea family, it's all the same thing. These are really good examples of plants that do this biological fixation. Peas, peanuts, beans, any of those things, they're all very good at biological fixation. They're all very good at being able to take nitrogen just within the atmosphere and convert it into this usable form, where then it's a element that we can then use, because nitrogen is something that's extremely important to us and to plants. It's one of the minerals that we need to survive. And so we need nitrogen. And the plants do this through a mutualistic symbiotic relationship. So in this type of symbiosis, both organisms of different species will rely on one another for nutrients, protection, and other life functions. And they are usually found living close together in proximity. So this mutualistic symbiotic relationship that happens between the rhizobia, so between some bacteria and the plants. And the bacteria and the plants live together. The bacteria basically lives on the plants. And the plants provide the food, and the bacteria provides this fixation process and being able to provide the nitrate. And so it's this nice symbiotic relationship. Here, you can have energy, you give me the nitrogen, perfect. I give you a place to live, you give me nitrogen, I give you food. Works out for everybody. Mutualistic symbiotic relationship. So then we have two parts, because we talked about the idea that this is going to go from an abiotic form to a biotic form, but then it's cycling. So it's a process where it's going to go full circle. So then it's also got to go from biotic to abiotic. And so what we're going to call that when it's going from abiotic or from non-living to living, we're going to call that nitrification. So then, if we are going the opposite way and going from living to non-living, denitrification. And so that's the conversion of nitrates back into the gaseous N2 form. And that's going to happen through bacteria or through organic matter being burned is another way that we can get the denitrification process to happen. And so in trying to put this all together, so we got the flow of energy, we get this continuous input, it's not recycled, it's just energy being converted, starts at the sun, radiant energy, through photosynthesis, taken in by producers, then taken in by consumers, then maybe taken in by other consumers or taken in by decomposers, and then all of those things are giving off heat through cellular respiration. So it flows through the ecosystem, enters as the sunlight exits as heat. Then with the chemical cycling part, we get our carbon and our nitrogen and other chemicals being recycled in the ecosystem, in the biosphere. Specifically, we focused on nitrogen and the idea of the nitrification and denitrification process. The idea of taking nitrogen from its abiotic form to its biotic form, and then back from biotic form to its abiotic form. And all of that becomes important because the chemicals and these elements, these minerals, they're able to be used over and over again. And that the idea of how important soil is going to be in that process is something that we'll then talk about in a future lecture as well. But why are both of these things important, and why talk about both of them together? It's because they both relate to patterns of feeding within the ecosystem. We talked about the food chain and trophic structure and what happens in terms of trophic cascades and ecosystem simplification if you have problems with that structure. And with our chemical cycling, we also have our fungi and our bacteria and our microorganisms and all these different little things in the soil that need this chemical cycling to happen in order for them to be able to find their structure and function within the ecosystem as well. And so we have all these different things coming together in the ecosystem. So the next thing that we're going to focus on in this class is to talk about the ecosystem and ecology, and really get into how do all these things tie together.